In our last video, we introduced the idea of a quadratic, so something squared, and we had a geometric interpretation of it and so forth. So now we're going to use that as the context in which to introduce this diagonalization process. So we're going to start with the context of the quadratic, which is a real symmetric matrix A, in order to understand the steps, and then we'll see in the next couple videos how we can extend this to a broader case. So we have our original variables, the x variables, x1 through xn, and those define a coordinate system on which our quadratic sits. And what we're going to imagine is we can transform that coordinate system from x to y, so a new set of variables y1 through yn, with respect to which the quadratic is going to be in its canonical or standard form. So we can imagine that that is accomplished through some transformation matrix. We'll call it Q. I don't know what Q is yet. We'll talk about what that is, and based on the notation you might be able to guess what it is. But there's some Q such that x equals Q times y is going to accomplish that rotation in order to put the quadratic in its standard form. So let's take a look at our quadratic in terms of x, and for it to be a quadratic in terms of y with a diagonal matrix, what does that mean for how the Q is used? So we have our original quadratic, A is x transpose times A times x, but now x is Q times y, x is Q times y. Remember, the transpose of the product is the product of the transposes, but in reverse order. So the transpose of Q times y is y transpose times Q transpose. So now I have y transpose times something times y. Well, that would be a quadratic if this something in the middle is indeed an n by n matrix, which it has to be based on the sizes of these matrices. So for it to be a diagonal matrix, however, that would mean that this piece in the middle, the Q transpose times A times X, needs to be a diagonal matrix D. In that way, our new quadratic y transpose times d times y is indeed in its canonical or standard form. So the diagonal matrix D comes from Q transpose times A times Q. Great, so I still haven't said what Q is. We'll do that in the next slide. But I do know that there is such a Q, that the Q transpose times A times Q will produce a diagonal matrix D. All right, so we say that Q diagonalizes A. Q is the matrix. We'll call it the modal matrix for reasons you'll see in a later video. The modal matrix is such that it diagonalizes A. It takes the original A, which is a full real symmetric matrix, and converts it into a diagonal matrix D. So here's the procedure, and then I'll show you that it does indeed diagonalize as we've just described. So as you might guess, it involves getting eigenvalues and eigenvectors. And so we do that. We get the eigenvalues. We get the corresponding eigenvectors. Now this is a real symmetric matrix A. So remember the properties from earlier in this section. So we know that if we have distinct eigenvalues, we have eigenvectors which are mutually orthogonal. If they are not distinct, so if they're repeated, we can choose the constants such that the eigenvectors are also mutually orthogonal. So that's why we're going to use the Q notation. Now I normalize them to length 1. So what I get are the orthogonal eigenvectors of the original matrix, and then we're going to normalize them to length 1 so that they are orthonormal eigenvectors of A. So now we have our eigenrelations that relate the lambdas with the Q's. So AQ1 is lambda1 Q1, AQ2 is lambda2 Q2, and so forth. So Q is an orthogonal modal matrix, and that's why we use the nomenclature Q. It is an orthogonal matrix, so it has this property that its transpose equals its inverse, as well as some other properties that we'll talk about in the next section. So we simply form Q, which is n by n, same size as A, by putting in as the columns the orthonormal eigenvectors of A. So Q1 in the first column, Q2 in the second, through Qn. The order doesn't matter in the sense that it's still an orthogonal matrix. It'll still do the diagonalization. The only difference will be how the corresponding eigenvalues are ordered in the diagonal matrix that will result. So let's show that indeed Q transpose times A times Q does do this diagonalization, and we'll see exactly what D is. And I just hinted at it a moment ago. It turns out to be very nice. So let's start with A times Q. So A times Q, here's the Q, with the columns being the orthonormal eigenvectors of A. And then we're going to write the A matrix row-wise. So little a1 is going to be the first row, a2 is the second row, a3 is the third row, and so on of A. Then I take the product, the matrix product. So remember how matrix products work from chapter 1. So in the 1, 1 position of the product, I take the first row, inner product with the first column. So that's inner product of A1 with Q1. In the 1, 2 slot, we have the first row of the first and the second column of the second, inner product of A1 with Q2. Continue that all the way through all those inner products to fill up the matrix product that we have here. Now if we look at this closely, look at this first column. The first column is inner product of A1 with Q1, A2 with Q2, A3 with Q3. So that's just a vector A times Q1. And if you don't quite see that, just work backwards. Just take our A, written row-wise like we did here, and take the product of that with the vector Q1, and you'll see that indeed it's equal to this series of inner products. Same thing with the second column. That's the vector AQ2. But from the eigenrelations, AQ1, well, that's just lambda 1 Q1. HQ2 is just lambda 2 Q2. So now we have our matrix A times Q. The columns of that product are just the eigenvalue times its corresponding orthonormal eigenvector, 1, 2, 3, through n. Now let's pre-multiply by Q transpose and see what happens. So here's our A times Q that we just had from the last slide. And now we pre-multiply Q transpose. So now that has Q1 as the first row, Q2 as the second, Q3 through Qn. Again, do the matrix multiplication. In the 1, 1 position, we have the first row, first column, take the inner product. That's lambda 1 times the inner product of Q1 with itself. Q1 with itself. In the 1, 2 slot, so right here, take the first row, second column. That's lambda 2 times the inner product of Q1 with Q2. Once again, follow all the way through to all those inner products in the matrix multiplication. So now watch what happens. The inner product of any Q with any other Q. Remember, these are orthonormal vectors. They're orthogonal to one another. So that means that the inner product of any one of these vectors with one of the other vectors is 0. So this inner product vanishes, all of these vanish, this one vanishes, these vanish. All of the off-diagonal terms become 0 because it involves an inner product of one Q with another, one orthogonal eigenvector with another. Then look at the main diagonal, inner product of Q1 with Q1, Q1 with Q2. What are those inner products? Well, those are the same vector. They've been normalized to length 1. So their inner products are just 1. So notice what happens. The main diagonal elements are just lambda 1, lambda 2, lambda 3, through lambda n. So indeed, we get a diagonal matrix D such that the eigenvalues are sitting right on the diagonal with zeros on the off diagonals. Okay, so we've shown that Q transpose times A times Q, where A is real symmetric, Q is the modal matrix comprised of the orthonormal eigenvectors as the columns. Q transpose times A times Q does indeed produce a diagonal matrix. Not just any diagonal matrix, it has the eigenvalues sitting on the diagonal. All right, so let's make a number of comments about this. First of all, you'll notice that if we write this out as a quadratic, now in terms of y, the new variable y, so y transpose times d times y, it is indeed in canonical form. It's just a coefficient times y1 squared plus a coefficient times y2 squared. and the coefficients are the eigenvalues. So this is really powerful, and that's all going to carry over, as we'll see. So one of the great things about this is I don't actually have to evaluate Q transpose times A times Q. Once I have the eigenvalues, I know what D is. I know what Q transpose times A times Q is. It's just a diagonal matrix with the lambdas down the diagonal. I still need the Q, so I do need to get the eigenvectors because I need to do the transformation back and forth between X and Y. But in terms of getting D, all I need to know is the eigenvalues. Once again, just emphasize, the order of the eigenvalues, how they appear in D, corresponds to how you put the Q's into form your big Q, your capital Q. So if you make a different choice than I do, our eigenvalues will be in different locations, but it's still in canonical form. So again, just to remind us, one of the properties of orthogonal matrices is that the Q transpose is equal to the Q inverses. And this is going to become important when we generalize this to the non-symmetric case. So in this case, Q is our modal matrix, but not only that, it's orthogonal. The reason why I wanted to introduce diagonalization within this context, even though it's a special case, it's in a little corner of the sandbox where you have real symmetric matrix A. The reason why I wanted to do this because now we can think of diagonalization in this geometric fashion. We have a quadratic, such as an ellipse, and I'm rotating the coordinate system such that in terms of the new coordinate system, the major and minor axes of the ellipse, or whatever the quadratic is, align with the coordinate axes, and it's in the canonical form. So now we have this geometric image, geometric intuition for what diagonalization is doing. So in subsequent videos and subsequent sections, when we apply this to more general cases, we have this intuition built in. So, and then this is important. So when you think of diagonalization, actually you should not think of what we just did in terms of Q transpose times A times Q. We're going to generalize this, and that generalization should be the way you think of diagonalization. So the danger of doing this first is we think this is diagonalization, but I just want to give us this intuition before we get into the more general situation. The rest of this section I won't go over in this video, but what it does is it just re-encapsulates what we did in one of the previous videos, looking at systems of linear algebraic equations where A is real and symmetric and how we can use the properties of real symmetric matrices to solve it. It goes through the same process, but it uses this matrix notation with the Q's and the A vectors and so forth. You end up with the same thing in the end. The vector of these coefficients, the A coefficients, is equal to these inner products divided by the lambdas. So that is literally just doing that same process, but now in the matrix notation that we've just developed. Not terribly important, but useful to be aware of.